In physics, mass is a property of a physical body which determines the strength of its mutual gravitational attraction to other bodies, its resistance to being accelerated by a force, and in the theory of relativity gives the mass-energy content of a system. The SI unit of mass is the kilogram. Mass is not the same as weight. Even though we often calculate an object's mass by measuring its weight with a spring scale instead of comparing it to known masses, an object on the Moon would weigh less than it would on Earth because of the lower gravity, but it would still have the same mass. For everyday objects and energies well described by Newtonian physics, mass describes the amount of matter in an object. However, at very high speeds or for subatomic particles, special relativity shows that energy is an additional source of mass. Thus, any stationary body having mass has an equivalent amount of energy, and all forms of energy resist acceleration by a force and have gravitational attraction. There are several distinct phenomena which can be used to measure mass. Although some theorists have speculated some of these phenomena could be independent of each other, current experiments have found no difference among any of the ways used to measure mass. Inertial mass measures an object's resistance to being accelerated by a force. Active gravitational mass measures the gravitational force exerted by an object. Passive gravitational mass measures the gravitational force experienced by an object in a known gravitational field. Mass energy measures the total amount of energy contained within a body, using E equals mc2. The mass of an object determines its acceleration in the presence of an applied force. This phenomenon is called inertia. According to Newton's second law of motion, if a body of fixed mass m is subjected to a single force F, its acceleration a is given by F per meter. A body's mass also determines the degree to which it generates or is affected by a gravitational field. If a first body of mass m is placed at a distance r from a second body of mass mb, each body experiences an attractive force Fg equals gmamb, r2, where g equals 6989667000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 universal gravitational constant. This is sometimes referred to as gravitational mass. Repeated experiments since the 17th century have demonstrated that inertial and gravitational mass are identical. Since 1915, this observation has been entailed a priori in the equivalence principle of general relativity. Units of mass. The standard international system of units unit of mass is the kilogram. The kilogram is 1,000 grams, first defined in 1795 as 1 cubic decimeter of water at the melting point of ice. Then in 1889, the kilogram was redefined as the mass of the international prototype kilogram, and as such is independent of the meter, or the properties of water. As of January 2013, there are several proposals for redefining the kilogram yet again, including a proposal for defining it in terms of the Planck constant. Other units are accepted for use in SI. The ton is equal to 1,000 kg. The electron volt is a unit of energy, but because of the mass-energy equivalence it can easily be converted to a unit of mass, and is often used like one. In this context, the mass has units of eV, c2. The electron volt is common in particle physics. The atomic mass unit is 1/12 of the mass of a carbon-12 atom, approximately 69731660000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 convenient for expressing the masses of atoms and molecules. Outside the SI system, other units include: the slug is an imperial unit of mass similar to the kilogram. The pound is a unit of both mass and force, used mainly in the United States. In scientific contexts where pound and pound need to be distinguished, SI units are usually used instead. The Planck mass is the maximum mass of point particles. It is used in particle physics. The solar mass is defined as the mass of the Sun. It is primarily used in astronomy to compare large masses such as stars or galaxies. The mass of a very small particle may be identified with its inverse Compton wavelength. The mass of a very large star or black hole may be identified with its Schwarzschild radius. Definitions of mass. In physical science, one may distinguish conceptually between at least 7 different aspects of mass, or 7 physical notions that involve the concept of mass. Every experiment to date has shown these 7 values to be proportional, and in some cases equal, and this proportionality gives rise to the abstract concept of mass. The amount of matter in certain types of samples can be exactly determined through electrode deposition or other precise processes. The mass of an exact sample is determined in part by the number and type of atoms or molecules it contains, and in part by the energy involved in binding it together. Inertial mass is a measure of an object's resistance to changing its state of motion when a force is applied. It is determined by applying a force to an object and measuring the acceleration that results from that force. An object with small inertial mass will accelerate more than an object with large inertial mass when acted upon by the same force. One says the body of greater mass has greater inertia. Active gravitational mass is a measure of the strength of an object's gravitational flux. Gravitational field can be measured by allowing a small test object to freely fall and measuring its free fall acceleration. For example, an object in free fall near the Moon will experience less gravitational field, and hence accelerate more slowly than the same object would if it were in free fall near the Earth. The gravitational field near the Moon is weaker because the Moon has less active gravitational mass. Passive gravitational mass is a measure of the strength of an object's interaction with the gravitational field. Passive gravitational mass is determined by dividing an object's weight by its free fall acceleration. 2 objects within the same gravitational field will experience the same acceleration. However, the object with a smaller passive gravitational mass will experience a smaller force than the object with a larger passive gravitational mass. Energy also has mass according to the principle of mass-energy equivalence. This equivalence is exemplified in a large number of physical processes including pair production, nuclear fusion, and the gravitational bending of light. Pair production and nuclear fusion are processes through which measurable amounts of mass and energy are converted into each other. In the gravitational bending of light, photons of pure energy are shown to exhibit a behavior similar to passive gravitational mass. Curvature of space-time is a relativistic manifestation of the existence of mass. Curvature is extremely weak and difficult to measure. For this reason, curvature was not discovered until after it was predicted by Einstein's theory of general relativity. Extremely precise atomic clocks on the surface of the Earth, for example, are found to measure less time when compared to similar clocks in space. This difference in elapsed time is a form of curvature called gravitational time dilation. Other forms of curvature have been measured using the Gravity Probe satellite. Quantum mass manifests itself as a difference between an object's quantum frequency and its wave number. The quantum mass of an electron, the Compton wavelength, can be determined through various forms of spectroscopy and is closely related to the Rydberg constant, the Bohr radius, and the classical electron radius. The quantum mass of larger objects can be directly measured using a Watt balance. In relativistic quantum mechanics, mass is one of the irreducible representation labels of the Poincare group. Weight versus mass. In everyday usage, mass and weight are often used interchangeably. For instance, a person's weight may be stated as 75 kg. In a constant gravitational field, the weight of an object is proportional to its mass, and it is unproblematic to use the same unit for both concepts. But because of slight differences in the strength of the Earth's gravitational field at different places, the distinction becomes important for measurements with a precision better than a few %, and for places far from the surface of the Earth, such as in space or on other planets. Conceptually, mass refers to an intrinsic property of an object, whereas weight measures an object's resistance to deviating from its natural course of free fall, which can be influenced by the nearby gravitational field. No matter how strong the gravitational field, objects in free fall are weightless, though they still have mass. The force known as weight is proportional to mass and acceleration in all situations where the mass is accelerated away from free fall. For example, when a body is at rest in a gravitational field, it must be accelerated by a force from a scale or the surface of a planetary body such as the Earth or the Moon. This force keeps the object from going into free fall. Weight is the opposing force in such circumstances, and is thus determined by the acceleration of free fall. On the surface of the Earth, for example, an object with a mass of 50 kilograms weighs 491 newtons, which means that 491 newtons is being applied to keep the object from going into free fall. By contrast, on the surface of the Moon, the same object still has a mass of 50 kilograms but weighs only 81.5 newtons. Because only 81.5 newtons is required to keep this object from going into a free fall on the Moon. Restated in mathematical terms, on the surface of the Earth, the weight W of an object is related to its mass m by W equals mg, where g equals 7009806650000000009.806665 meters per square second is the acceleration due to Earth's gravitational field. For other situations, such as when objects are subjected to mechanical accelerations from forces other than the resistance of a planetary surface, the weight force is proportional to the mass of an object multiplied by the total acceleration away from free fall, which is called the proper acceleration. Through such mechanisms, objects in elevators, vehicles, centrifuges, and the like may experience weight forces many times those caused by resistance to the effects of gravity on objects, resulting from planetary surfaces. In such cases, the generalized equation for weight W of an object is related to its mass m by the equation W equals ma, where a is the proper acceleration of the object caused by all influences other than gravity. Macroscopically, mass is associated with matter, although matter is not, ultimately, as clearly defined a concept as mass. On the subatomic scale, not only fermions, the particles often associated with matter, but also some bosons, the particles that act as force carriers, have rest mass. Another problem for easy definition is that much of the rest mass of ordinary matter derives from the invariant mass contributed to matter by particles and kinetic energies which have no rest mass themselves. From a fundamental physics perspective, mass is the number describing under which the representation of the little group of the Poincare group a particle transforms. In the standard model of particle physics, this symmetry is described as arising as a consequence of a coupling of particles with rest mass to a postulated additional field, known as the Higgs field. The total mass of the observable universe is estimated at between 1052 kilograms and 1053 kilograms, corresponding to the rest mass of between 1079 and 1080 protons. Inertial versus gravitational mass. Although inertial mass, passive gravitational mass and active gravitational mass are conceptually distinct, no experiment has ever unambiguously demonstrated any difference between them. In classical mechanics, Newton's third law implies that active and passive gravitational mass must always be identical. But the classical theory offers no compelling reason why the gravitational mass has to equal the inertial mass. That it does is merely an empirical fact. Albert Einstein developed his general theory of relativity starting from the assumption that this correspondence between inertial and gravitational mass is not accidental, that no experiment will ever detect a difference between them. However, in the resulting theory, gravitation is not a force and thus not subject to Newton's third law. So, the equality of inertial and active gravitational mass remains as puzzling as ever. The equivalence of inertial and gravitational masses is sometimes referred to as the Galilean equivalence principle, or the weak equivalence principle. The most important consequence of this equivalence principle applies to freely falling objects. Suppose we have an object with inertial and gravitational masses m and m, respectively. If the only force acting on the object comes from a gravitational field g, combining Newton's second law and the gravitational law yields the acceleration. This says that the ratio of gravitational to inertial mass of any object is equal to some constant k if and only if all objects fall at the same rate in a given gravitational field. This phenomenon is referred to as the universality of free fall. The first experiments demonstrating the universality of free fall were conducted by Galileo. It is commonly stated that Galileo obtained his results by dropping objects from the Leaning Tower of Pisa, but this is most likely apocryphal. Actually, he performed his experiments with balls rolling down nearly frictionless inclined planes to slow the motion and increase the timing accuracy. Increasingly precise experiments have been performed, such as those performed by Laurent-Diotvos using the torsion balance pendulum in 1889. As of 2008, update, no deviation from universality, and thus from Galilean equivalence, has ever been found, at least to the precision 10⁻12. More precise experimental efforts are still being carried out. The universality of free fall only applies to systems in which gravity is the only acting force. All other forces, especially friction and air resistance, must be absent or at least negligible. For example, if a hammer and a feather are dropped from the same height through the air on Earth, the feather will take much longer to reach the ground. The feather is not really in free fall because the force of air resistance upwards against the feather is comparable to the downward force of gravity. On the other hand, if the experiment is performed in a vacuum, in which there is no air resistance, the hammer and the feather should hit the ground at exactly the same time. This can easily be done in a high school laboratory by dropping the objects in transparent tubes that have the air removed with a vacuum pump. It is even more dramatic when done in an environment that naturally has a vacuum, as David Scott did on the surface of the Moon during Apollo 15. A stronger version of the equivalence principle, known as the Einstein equivalence principle or the strong equivalence principle, lies at the heart of the general theory of relativity. Einstein's equivalence principle states that within sufficiently small regions of space-time, it is impossible to distinguish between a uniform acceleration and a uniform gravitational field. Thus, the theory postulates that the force acting on a massive object caused by a gravitational field is a result of the object's tendency to move in a straight line and should therefore be a function of its inertial mass and the strength of the gravitational field. Origin of mass in theoretical physics. A mass generation mechanism is a theory which attempts to explain the origin of mass from the most fundamental laws of physics. To date, a number of different models have been proposed which advocate different views at the origin of mass. The problem is complicated by the fact that the notion of mass is strongly related to the gravitational interaction, but a theory of the latter has not been yet reconciled with the currently popular model of particle physics, known as the Standard Model.